So if you still remember in the previous video, we actually talked about the not previous video, previous two videos, we talked about low pass filter and zeroth order whole, somewhat briefly. And we say that if you are actually not interested in the phase shift of your system, because if you don't want to phase shift anything, actually low pass filter can be used. Alright, so in order to do that, or in order to discuss how do we use the low pass filter, we're gonna know how to transform your low pass filter. Okay, because in some sense, if you are not interested in shifting of your signal, low pass filter is a good way, because you just want the low pass filter. The purpose of it is just to trim, is to prevent a aliasing issue in a cheaper way. Because if you want to ×2 your frequency, alright, you may actually incur more costs. And I think I may be wrong, I don't know, because come to think about it, because your low pass filter is equals to A over S plus A. A is 2 over T. Okay, so to some sense, these two give me a more intimidating portion, where I don't know whether these two will really affect the frequency also. So I can't confirm that that low pass filter may not require 2 times. Alright, but to a certain extent, I would highly believe in my current situation right now that low pass filter no need ×2 frequency. Alright, ×2 of original frequency. Alright, so you can carry on with your sampling frequency, just that you will choose your low pass filter frequency such that you will remove the aliasing effect, so you can prevent this thing from happening over here. Okay, so I hope that this is pretty much a bit clear before I go on to low pass filter. So the low pass filter purpose is to clean the signal a bit and prevent aliasing. So therefore, in order to do that, we use this one. So your low pass filter is equals to this, and our purpose is actually to transform your low pass filter into a transfer function in the Z domain. So therefore it's Hz over output over input equals to output over input, sorry. And therefore, if you remember, your transfer function in the S domain is Gs, so in the Z domain is H of Z lah. So what we can do in the first step is what? We just write in terms of the transfer function of U of S over E of S first. Okay, this is your output over input in the S domain. Alright, because A over S plus A is actually in the S domain. Okay, so what we can do now is simply to bring this S plus A to this side, bring this E of S to this side. Alright, so what I have is US times S plus A, alright, equals to A over A times ES. So this thing times this thing times this thing. Okay, next I multiply inside, so I have this thing over here, you see. So US times S, I have SUS, US times A, I have AUS. The AES is simply same. Okay, now I inverse Laplace, I have this thing, alright, and then I shift this inverse Laplace. SUS becomes U dot T. Okay, this is something that you may need to familiarize with if you forgot or whatever. Alright, taking note that our initial condition is equals to 0. Alright, this is called partial control. Alright, in our whole course we are talking about partial control. So we actually deal initial condition as 0 to simplify things quite a lot. And therefore SUS is equals to U dot T lah. Alright, where your US is UT, your ES is ET. Okay, just simply to inverse Laplace your time domain. And then after that you shift your AUT over to this side, you have this thing over here. So your U dot T is equals to this stuff. Alright, so what we can do is to bring this thing, it's the same thing actually. I'll just copy lah, okay, because I have no space in my paper already. I'll just copy this, I paste it in another sheet of paper. You see the font size is so big, that's why I take in a lot of space. But it's the same thing, like U dot T is this one, I didn't cheat a feeling. Alright, so I just simply continue from here right now. Alright, so in order to do this, I want to set up in terms of UT. Okay, so what I can do is, this is differentiation. So if I were to bring this differentiation to this side, this whole thing will become integration. Right, I think you get what I mean. Okay, so in other words, in order to find UT, I need to integrate this thing. That's all. Okay, so what I do is to integrate lah. Okay, so dt, alright, from 0 to your whatever frequency that you want. We call this the KT. Okay, and because this is in the time domain, Alright, we are dealing with the digital domain. We are going to change the t into tau. Alright, so I have u tau. So I just simply change the tau. Right, so we have all this tau over here. Okay, indicating that we are trying to deal in terms of the digital domain. Alright, because the integration domain, if you want to integrate, you can straight away integrate. Alright, you don't need to do anything. But for the digital system, if you still remember, your digital systems is built by points. So if you want a new point, you need information of the previous one all along, right? You need all these points in your equation to formulate this particular point. You need the previous information. So therefore, you need the previous information. You're gonna have a lot of stuff, alright? And you're gonna split your integration into many steps, alright? And for example, so for example, you'll have 0 to 1 plus 1 to 2 plus integration 2 to 3, and then from whatever to infinity, blah blah blah. Okay, so you all the way to whatever thing that you want, your particular frequency that you want to look at. So you're trying to formulate the particular phenomenon for you now. Alright, in order to do that, I'll just write as 0 kt. I'll write this whole thing over here. Alright, I set it as equals to a smiley face. Okay, I'll set it as a why am I drawing? Yeah, a smiley face. Alright, yeah, like this. Okay, so this is the first integration, d tau, in terms from 0 to kt first. Alright, plus, okay, from this is not kt. Hold on a while. From 0 to k minus 1t. Okay, or you can write as kt minus t. Alright, but because I want to show that it's more clearer, so I'll just write as k minus 1 times t. Okay, and this integration from k minus 1 to t to your kt plus, alright, the rest are the same already. Okay, this thing over here is your equation lah, d tau. This one, I'll just write it as a smiley face. Alright, and over here I'll just continue to paste until you reach your particular signal that you want, alright, some signal, alright, whatever kt. For example, if you want your k to be maybe 10, then when you reaches 10, this is your full integration. Alright, so if you have to zoom out a little, you have 10 times of this one, or 11 times, I don't know, but you're gonna add up all of them all together if k equals to 10. Okay, so in order to show you the particular information like 0 to 1 and then 1 to 2, 2 to 3, etc., I'm gonna sub in my k so that you can visualize things. So if my k is equals to 1, for example, I start from 1, if you start from 0, no point, right? So if my k is equals to 1, my first signal, I sub it in over here. 1 minus 1 is 0. So integration from 0 to 0, this thing is just 0. Alright? Then I don't think, anyway, at time k equals to 1, you may have, although this integration may be 0, but you may have certain values over here. Alright, because this will tell you your initial condition. Okay, but in this case, since we know that initial condition is somewhat not in our concern, so this is sometimes normally 0 to some extent. Alright, don't believe in me because yeah, but anyway, if k equals to 1, this thing will become 0. But if you still remember your integration, if your equation is 2t plus 3, if this thing becomes 0, at least this thing over here is still some values. Alright, so therefore I think you get what I mean lah. But anyway, this is initial condition lah. Okay, this is when k equals to 1, and then when k equals to 2, this thing becomes 2 minus 1, which is 1. Then this time will be 2, right? So it's from 1 to 2. Alright, then over here when k equals to 3, then this is from 3 minus 1 is 2, then this is 3. So as you can see, it's from 1 to 2, 2 to 3. At first it's 0 to 0 lah. Okay, and things like that. And then 3 to 4, 4 to 5, all the way to whatever that you want. Alright, so in order to make things simple for us in this case, as a general equation, I'll just simply remove all these things, because we know that is this thing over here will continue until you reach your KT. Alright, so I hope that this is pretty much clear in this manner. Therefore, instead of this smiley face now, alright, I can actually remove this smiley face and replace back my equation. Okay, I lazy to, yeah. So I'll just show you lah. I'll just paste this equation over here. Okay, so when I paste this equation, I can integrate them. Alright, so if I were to integrate this thing over here, I'll not do it for you because I don't think it's necessary. I just want to prove to you certain stuff of the equation lah. Alright, because in the future maybe you need lah. But I'll just leave it here plus. Alright, I'll have A. Alright, so am I doing the right thing? Hold on a while. I don't think you can derive that. I don't think you can derive this thing because you need some equation of E. But the general thing is that this thing over here, actually, if you come to think about it, is actually uk minus 1t. Alright, so this thing over here is somewhat like a u in terms of k minus 1t, something like that. But anyway, just to inform you about that, because in the end, maybe in the future, you might need to do these things again or whatever. But anyway, so at over here, alright, this thing over here, I'll just write it as AE, alright, k minus 1 minus u k minus 1, alright, and then do I need t? I think I need t. Alright, this is t, this is t. Okay, yeah. Alright. So therefore this is the case. Okay? Yeah. So don't ask me why do we do this. I also don't know why do we do this. But this thing over here becomes this one, while this thing over here becomes this. Okay, your A is here, your E tau becomes ek minus 1t. Okay, this is t lah, okay? Minus your, maybe I should put t, this is your AU tau, it becomes uk minus 1t. So your A is being factorized out already lah, just to inform you. A over here is factorized out over here, while your E tau is this one, minus away your ut, which is this one. That will makes more sense. Okay, so what we can do now, actually this is your u tau, if you still remember. Right, this is your u tau. We integrate all the stuff, we have this thing. Okay, alright, so now we're gonna z transform your this thing over here. Alright, you're gonna z transform your u tau into uz. So in this case, I think your u tau is actually somewhat kt equals to tau, something like that. I don't know. Alright, just whatever thing I know, I just whack over here. Okay, but anyway, this is tau. Where if you z transform becomes z lah. So over here, this is something like a lagging. So it's something like a k minus 1t also. Okay, so over at this side, this is obviously a lagging. Alright, so in this case, we can write this uk minus 1 as uz. This lagging k minus 1 I'll just write as z minus 1. Okay, yeah, okay, correspond to what I've written. Alright, this t over here is, wait I think I'll just place this t over here as over here, because in what I've derived, I don't think I see this t. But anyway, let's put this t over here, because over here is this one, right? It's most obvious, but we have a t over here. I think we should put in the t lah. But in case that I'm wrong, I'll just leave it as that first. And then this over here is, I just multiply my a inside. I don't know why they factorize it out, but anyway, so of AE, instead of small e, I'll just write capital E with a lagging of z minus 1 t also. Okay, minus, alright, u a, because a multiplied inside already. Okay, so I have a z minus 1, alright, u z, okay, and then t. So this thing over here is being placed over here, with knowing that your a is multiplied into them. Okay, take note of that. Alright, and the reason why I keep this t is because in my paper I see that derived t, so I think I've carelessly forget to rewrite this t over here. But anyway, let's continue with this thing. Alright, let's continue with this. So therefore, what I can now rearrange is that I can group what? What can I group with these things? I can group my uz and my uz all at one side, because this is also uz. So let's kind of group everything as one at one side. So what I have is uz, which is this one. Alright, minus away this portion. Okay, so I'll just simply bring this down. Sorry, okay, because this thing over is positive, bring here is negative. Alright, this thing over here is negative, I'll bring it over here, it becomes positive. So I have plus. Alright, and I'm gonna copy this. Is equals to, where my pen, is equals to this thing over here. So I'll just also copy it. Alright, so I'll just copy this thing and put it all over here. Alright, so I have this thing now. Pretty cool, huh? Alright, so now I can factorize out my uz already. Alright, I can factorize my uz because they are all the same. Alright, so if I were to factorize out my uz, I have 1 minus, alright, z minus 1t plus, alright, a z minus 1t. Okay, so the uz is being removed, and removed. Alright, you just compare. This thing becomes here. Alright, this thing becomes here. Your t all is all over here. Alright, hope you understand what I mean. Pretty clear, I think. Yeah. Anyway, so while this thing over here, I keep it kind of like cool. I put it over here. Aha. So as you can see, we are nearing. We have uz and we have ez over here. So I'll just bring this ez down. So what I have is uz, ez, okay, is equals to what? Alright, is equals to the numerator, which is az minus 1t, right? So I'll just write it as a, maybe I should put it over here, az minus 1t over, so I'm gonna bring this all the way down, right? Yeah, so I'll just become like this. Ta-da! Ora. Okay, so therefore over here I'll just rewrite the top part as ez minus 1 over t. I mean this one is equals to this one. I just group this thing. Just group this z minus 1 at one side. So I have z minus 1, alright, with the t also, okay. And then if I were to factorize out this whole thing, I will have 1 plus. This is the point where this t comes in. Alright, my red color one, if you still remember. This, maybe you can click back about 5 minutes or 6 minutes ago. Alright, this t I just put in because over here the t are being brought inside. You see? But up to this point, but because of this thing, this t I actually bring in because I thought that these t's are in, so therefore this t must be also brought in. But however, this is not needed. This t also not needed. So all along this t is not needed at all. Alright, even this thing over here, if I were to bring it to some other side, if you still remember, we actually bring it to other part of the equation. I actually brought it up. I actually brought it to the other part already. But anyway, this thing over here is this thing, but I'll just remove the t also because this t is being removed. So all the way, if you all the way go down, this t over here is also removed. Okay? For some reason, I don't know. I'll leave you to think about it. But anyway, this z minus 1 and this z minus 1 over here is constant, so I'll just factorize them out. I'll have 1 plus at. Okay? Then if I were to rearrange, I multiply by, because this z minus 1 is 1 over z, right? So I'll just multiply by z over z. So what I will have is at, alright, z minus 1 plus at, I think. Is it? Because my purpose, I think this is pretty heavy video, but anyway, let's continue first now, because we're ending already. Our purpose is to get something like a over s plus a. Okay, in this case, I think it's a over z plus a, I think. Whatever, but anyway, our purpose is to somehow have this form. So we are nearer because at least you can see we are somewhere near. We just divide 1 over t divided by 1 over t. This thing over here is just 1. I'm just simply rearranging also. Alright, so over here is also times 1. I'm simply rearranging this stuff. Then next I rearranging again. Alright, what do I have? I have at times 1 over t is a, right? So z times 1 over t is zt minus 1 over t plus at times 1 over t is what? A, right? Yeah. So we are somewhat near already, right? So therefore I can rewrite this as a z minus 1 over t plus a. Aha! Therefore we have somewhat proved to you these things already. Okay? And this method is your forward rectangular method. Alright? And how does the forward rectangular method comes in? Is when you input your u. Okay? I have no idea why do I sub in as forward. When forward, I don't know why when in forward rectangular, I sub in as kt minus t. This u over here I sub in as this one, and ae over here I sub in as this one. If you want to check back where I have stopped just now, is the point where I sub in the integration, if you still remember. I actually told you the integration, the meaning behind the integration. Alright, and we also told you that we actually don't know how to derive up to here. Alright, we actually somewhat briefly go across it. Okay, but this kt minus t is the point where you differentiate, not differentiate, but rather than tell you that at this point onwards, this is your forward already. Okay, so if you just to recap lah, alright, the overall is that we set our, if you still remember, we set in our transfer function in the S domain at a over s plus a. We rearrange stuff, already, we inverse Laplace, we get a u dot t, alright, and then after that we bring this u dot t over here, and then we want to integrate it because this is u dot t, we want to put it in ut, we want to change it to ut, so we need to integrate this, and then after that we change it to the tau domain because we say that it's a digital domain, and then after that we integrate it where this is the point where we want to, before we integrate, we want to sub in, how do I say, after the integration, for some reason, you'll become a forward where you sub in as your ukt minus t over here, as you can see. Okay, and then after which we carry on with the z transform. So over here is the point where you sub in your stuff. This is the critical point where you determine your forward, your backward, or your trapezoidal. Alright, so in the next video, I'll just spend about 1 or 2 minutes to recap on these things, to amplify this thing a little while. While uz is equals to all this, and then we rearrange stuff and rearrange again and rearrange, we get this thing. So this is your representation of your low pass filter in the Z domain, where it is a forward low pass filter. Okay, this is a forward low pass filter. So the things go similar to low pass filter for your forward, backward, and your tastine or your trapezoidal. Mainly, the critical step is at this particular step. Alright, so in the next video, I'll just show you the comparison. See you there.